Hi everyone, my name's Paul Mitchison from Imperial College London, and it's a pleasure to be able to talk to you and give a tutorial here at Wireless Power Week. My talk is on an introduction to high frequency IPT, and in that sense, I hope you find it a nice follow-up to the talk that Duleepa and Grant have just given on inductive powering. And what I'm going to try and do here, therefore, is to give you a little bit of an insight as to what is specific to high frequency IPT systems, and sort of springboard off the work that they've done in their tutorial, and hopefully not repeat too much stuff because we don't have a lot of time. So, just a little bit about myself before we get into the technical details. I started working on inductive power transfer in probably about 2010, and it was sparked really by interest that I had that came from this photograph that I saw from MIT. This is actually, or at least a number of the people in this photo here went on to found Witricity. And what you see here is actually a demonstration of a high frequency IPT system. It's working at about 10 megahertz, and I'll talk a little bit about what I mean between the differences between high and low frequency IPT in a few moments. But for the moment, just accept this is what I would call a high frequency IPT system. You can see the transmit and the receive coils here. They're very basic in terms of construction. It's just copper wire and just a few turns wrapped on some former here, and there's polystyrene or something as the insulator. And they're able to get very good distance between the transmit and the receive coil. And that was the thing that caught my eye with this photograph. Now, of course, when I started looking at inductive power transfer and looking at the literature, then of course I realized that there's work going back a long way before this demonstration by MIT. But nevertheless, this particular photo is the one that really got me interested in the topic. So I'm going to talk to you about different aspects here, the main different aspects that you need for a high frequency inductive power transfer system, including the inductive link, but also looking at the primary side and the receive side circuits. So in power electronics, what we would call inverters and rectifiers. I'll talk a little bit also about regulations as well, but just to give you a heads up that there's also a dedicated talk on regulatory aspects here from Mauro Feliziani that you can see later on. As I say, I'm going to try and build on the work that you've already seen in the tutorial from Duleepa and Grant. And one of the things I want to do, first of all, is to try and show you why megahertz operation of these systems can be quite beneficial. So just to put some bounds on this, what is high frequency IPT? I mean, to an extent, it's all reasonably high frequency because all of the inductive power systems that you see, including the ones you may have on your mobile phone, the Qi standard and the SAE standard for charging of electric vehicles, they all work at reasonably high frequency. Those ones are typically operating at something like 85 kilohertz. Although in my world, we refer to that now as low frequency IPT, the kilohertz, the tens of kilohertz, 100 kilohertz type of operation. We refer to that as low frequency IPT, even if it's still a reasonably high frequency in the power electronics field. What I work on is inductive powering in the megahertz, and this is what I'm just broadly calling here a high frequency IPT. We work at 6.78 or 13.56 megahertz typically. These are the ISM bands, industrial, scientific and medical bands. They're unlicensed bands, and therefore they're free for us to use in this application. So whilst they look like fairly strange numbers for choice of frequency, it's due to regulatory aspects why we use those specific frequencies. The potential advantages of moving to high frequency over the 100 kilohertz types of systems are really demonstrated, I think, by that photograph that I've just shown you from MIT. You can get with these megahertz systems a very high distance, or really it's a transmit distance to transmit coil diameter ratio. That can be very high on these high frequency systems, and typically higher than it is on the kilohertz systems. In other words, you can transmit the power further. And the other aspect is the coils themselves tend to be very light. And that's simply because as you go to high frequency, you don't tend to use ferrite material in the systems. You don't need to, and I'll explain why that is in a couple of slides' time. So ultimately, lightweight and large distance, those are the reasons that drive us to high frequency rather than sticking at 100 kilohertz. It's not to say that that means that every application for IPT should move to megahertz. That's certainly not the case. However, there are definitely applications that Megahertz IPT is suited. There's a consortium for Megahertz IPT, and it's called the AirFuel Alliance. Okay, so let me talk first of all briefly about the inductive link itself. What you see here on this image is a primary and secondary coil that we built, actually the first system we built at Imperial, and this would be back in 2010, 2011, something like that. Not too dissimilar, as you can see, from the MIT system. Very simple coils here, just built out of copper turns. At that point, I think it's useful just to take stock and just to say, in terms of modeling of the inductive link itself and the operation of the inductive link, those of you that have a background in energy in some form, be it in power electronics or any course you may have done as an undergraduate in energy systems where you've looked at transformers, will have some basic background in transformer modeling. And it's useful just to very quickly review that. So you've got typically in a transformer, you have a former type component, the core, which is highly magnetically permeable and causes a high degree of flux linkage between primary and secondary, such that the fraction of primary flux that links with the secondary is almost 1. And we call that coupling factor. That coupling factor, therefore, can be written simply as phi12, that's primary flux that links with the secondary, divided by the total primary flux phi1. And as I say, in a transformer, that should be very close to 1. You can also write that coupling factor as the mutual inductance of the coils divided by the square root of the product of the self-inductances. So as I say, in a transformer, that value is very close to 1. In an inductive power system, you take away the former part of the transformer. You take away the core. You no longer have that flux guide between the primary and the secondary. That means that the fraction of flux from the primary that links with the secondary drops significantly. And the coupling factor in an IPT system, certainly in a high frequency IPT system, could be as low as about 5%. So about 5% is sort of a nominal figure that I would use for a high frequency IPT system. Something like 20% I think is pretty common in the lower frequency systems. And then for a transformer, it's very close to 1. You'll have then seen probably in your undergraduate material the equivalent circuit model of a transformer, and this is one that's often used in power engineering, and it has the concept here of coupling factor not being as high as 1 through the introduction of the primary and secondary leakage inductances. And what you can see here is that as you put a voltage on the primary of this circuit, if the primary leakage inductance is very low, then almost all of the input voltage is applied across the air gap and therefore can be used to transfer power to the secondary. If, however, the coupling factor is decreased, the primary leakage and the secondary leakage inductances will increase, the magnetizing inductance will decrease, and consequently only a small fraction of the input voltage appears across the air gap. And that's a problem because that can mean that we now have to drive very high voltages onto the primary in order to be able to get a reasonable voltage out of the secondary. It does not, however, automatically mean that low coupling means low efficiency. That is not true. If that was true, wireless power transfer systems would never be practical. So please note that it just, if you get a high leakage reactance here in a transformer-like component, what it's meaning is that you're not getting all of the voltage across the air gap voltage. All of the applied voltage is not appearing across the air gap voltage. We can deal with that. We deal with that with resonance, as you've seen in the previous talk. But it does not automatically mean poor efficiency. We don't tend to model wireless power transfer systems, however, using that transformer model. I show it there simply from the perspective of familiarity. we tend to model them as a coupled system as shown here, where we have two self-inductances and a coupling factor links those two self-inductances together. Those coils here have primary and secondary series resistances, just modeling the losses in the coils. And you can see here we drive a current into the primary, and that allows us to transfer power secondary. We tend to favor this type of model here in wireless power types of analysis for a couple of reasons. The easiest one is to say, well, if you simulate these systems in SPICE, then actually SPICE uses self-inductances and coupling factor as a way of modeling mutually coupled coils. It doesn't use leakage inductance and magnetizing inductance natively in the way that you would put this circuit into SPICE. The other thing is that LP and LS, as shown here, are the actual self-inductances of physical components. You can go and measure them. If you build a wireless power system, you can go and measure LP, you can go and measure LS. In a transformer, the circuit components in the model are not physical. You can't pull out and just measure, at least not very easily. You can't measure directly the magnetizing inductance and the leakage inductance. They're physically, it's one component, one inductor that is wound onto a core, and then we're separating them into their constituent parts in that model. We're not doing that here, where we are effectively achieving the same thing by using K rather than by splitting the inductor into separate inductors in the model. And those are reasons why we tend to use this model for inductive power transfer. Okay, so ultimately then, why are we interested in operating at high frequency? Well, I've already said to you, it's typically because we can get large distances between the coils at high frequency, and we can also achieve lightweight systems. Let's just see why that is. So the link efficiency of an IPT system, again, you've seen this in the previous talk, is k squared q1 q2 divided by 1 plus the square root of 1 plus k squared q1 q2 all squared. And if you plot that value of efficiency versus k squared q1 q2, as you can see here, once we've got k squared q1 q2 above about 10 to the 3, you can see we've got efficiency values of the link that are above 90%. And what this means is if we can get Q factors that are in the 1000, we can operate with a value of K, the coupling factor between the coils, that is only a few percent. So if we want to get big distances between the transmit and the receive coils, K is going to drop. There's not a hell of a lot we can do about that. But if we want high efficiency, we have to compensate. We have to compensate by increasing the Q factor. So how do we increase the K squared Q1, Q2? Well, as I say, large distance, K is going to drop. So we've got to maximize Q1 and Q2. And if you plot the Q factor of an inductor against frequency, well, you'll remember, I hope, that the Q factor of an inductor is omega L divided by R. So as you go up in frequency, omega L increases. Now, R also increases because of skin effect, but it doesn't increase as quickly, at least not to start with, as the omega L term. So if you increase the frequency, you'll get a higher Q factor. That's good for getting large distance and a good efficiency out of our wireless link. If you drive those coils at too high a frequency, however, eventually they will start to become antennas and they will radiate. And then the efficiency of the system will start to fall, as you can see here. So we've got a peak here. And as you can see here, it's for this particular coil that's being modeled, it's at around 10 megahertz, the peak. So if we operate at a few megahertz here, below that 10 megahertz peak, we'll have a very high efficiency of our system because we've got a very large Q factor. And you can see it's above, something like 10 to the 3, 10 to the 4 that looks to be achievable in terms of Q factor. So that is ultimately why we would like to move to high frequency. We can maximize Q1 and Q2, therefore we can work with a lower value of K, therefore we can get high distance between the transmit and the receive coils. Another effect, of course, is that means that we don't tend to use ferrite in these coils. We can get high values of omega L, high values of reactance of the coil, just by going to high frequency. We don't need to put ferrite in to get higher values of inductance or try to increase the Q factor. We do it purely with frequency. So we end up with fairly lightweight systems, as long as we can drive the coils at megahertz in an efficient way. In other words, we need circuitry on the transmit side and the receive side that can work well at megahertz. And that's really where the challenge is in making these megahertz IPT systems. So what are the differences then? Well, just to summarize, the differences between megahertz and kilohertz systems, obviously the frequency of excitation is different. The coupling factor is typically different. We typically operate with around 3 times less coupling factor in a megahertz system than a kilohertz system. That's fundamentally why I can get bigger distance between the coils in a megahertz system than I can in a kilohertz system. And I can do that because I can get a Q factor that might be something like 3 times higher in the megahertz system. That means that from a coil construction perspective, I tend to use air cored coils, whereas I put ferrite in the kilohertz systems. And also, as a consequence of the use or non-use of ferrite in a kilohertz system, the self-inductance of the coils can change as the relative position of the coils changes, because I have now flux linkage with the secondary coil, which may have ferrite material present. That's typically not the case in ferriteless systems, and perhaps in some cases can make dynamic systems easier at megahertz than at kilohertz. So let's move on then. Let me talk briefly now about the primary side drive circuits that we use at megahertz. There are a couple of issues that we need to bear in mind when we're designing the power electronics here to drive the primary coil. The systems, of course, have got to be efficient, so we need to minimize the loss in the devices. We've got conduction loss and switching loss. We would like to, of course, to minimize both of those. One of the ways of doing that is to move to wide bandgap components. So we use a lot of gallium nitride and silicon carbide in these designs. Switching loss in particular can be a problem. It's proportional to frequency, of course. So as you go to megahertz, switching loss can be a real issue. We try and reduce or almost eliminate that by using soft switching. The other thing that I note on here, the potential power factor of the system due to coil inductance means we need to try and create topologies where the semiconductors do not have to provide all of the VA product. In other words, if you think back to the equivalent circuit model of the transformer, I mentioned that the air gap voltage is only a small fraction of the applied voltage if the leakage inductance becomes very large. And ultimately, that is about VA rating. I don't want to have an excessive VA or particularly voltage rating of the semiconductors on the primary side, only to use a fraction of that rating to get the voltage across the air gap. And of course, you've seen how I deal with this problem. And as I mentioned earlier, we do that. We deal with that using resonance. So we want topologies that through resonance lower the VA ratings of the semiconductor devices. So inverters, we don't want to use hard switched topologies because that'll be very inefficient at megahertz. We don't want to use pulse width modulation in order to be able to shape a sine wave from a 2-level voltage source inverter, for instance, because if we want a megahertz fundamental, we need a 10 or 100 megahertz PWM in order to achieve that, and that's simply not going to be possible at these power levels. So soft switching inverters are what we're interested in at these frequencies. We can look at soft switch class D and class E types of inverter to minimize the power dissipation. Class D types of inverter are indeed popular in the lower power systems with Qi. One of the issues with them, of course, is that they require a floating gate drive. They can operate over a large load range, so there are some advantages as well, but they don't scale brilliantly into high frequency, particularly due to the fact that they've got to have that high side gate drive. And of course, they use more silicon. They've got at least 2 transistors, typically 4 transistors in an H-bridge configuration, as you can see here. So here's a resonant class D solution in a half bridge and a full bridge solution. There's a series capacitor with the transmit coil, which is just called L in this case. And you can get soft switching with these systems, but again, getting that to operate well at megahertz at decent power levels is really quite challenging. And as you can see, uses either 2 or more likely 4 transistors. These are the sorts of waveforms that you get here. You can see we produce a square wave voltage from the inverter, we get a sine wave current. And if you tune away from resonance, you get hard switching, as you can see in the second and third sequence of plots there. Not unexpected. That'll be true with all these systems. If you detune them, if you have soft switching at perfect tuning, you will move into hard switching as you move away from perfect tuning. So what is the solution that we therefore tend to employ at Megahertz? Well, it is these simpler, or perhaps they might look simpler, they might look more complicated to you because they might be topologies that you're not familiar with. This is a Class E topology. It's an inverter. It produces from Vin here, which is a DC voltage, it produces an AC voltage across the primary coil L2, and therefore an AC current in L2. And it does that with the resonant network here, the choke inductor L1, and it does it by switching transistor Q1 at the fundamental frequency. So if I want a 6.78 megahertz current flow in L2, that's a sine wave, I simply gate the transistor Q1 with a 6.78 megahertz square wave, turning that transistor on and off in switch mode. And if I tune the device properly, I can get zero voltage switching. You can see VDS on the right here. The transistor is switched off at 0 volts with a slow rate of rise of voltage due to the existence of C1 across the transistor. And that voltage naturally comes back down to 0 in a controlled way, at which point I can turn the device back on again. I've got zero voltage switching. I've got zero current switching when I turn the device on, but not zero current switching when I turn the device off, as you can see from the blue curve ID. This is an advantageous circuit because it now only has one transistor. The previous circuits had two transistors. This only has one. That's good for high frequency operation, particularly because it's a low side device. You don't have to worry now about very high frequency driving of high side devices. One of the things that you might do, and we've done in the past for improving the performance of these systems and minimizing the VA rating of the semiconductors, as I mentioned earlier, is to introduce the concept of semi-resonance. So you can see C3 has been added into this system here to operate the system at semi-resonance. This ultimately reduces the current rating of Q1 because now a large fraction of the tank current, the resonant tank current that must flow through the transmit inductor L2 in order to establish the magnetic field, now circulates within L2 and C3 and does not have to then flow through the Q1. So this parallel resonance here of C3, not operated at resonance, we still maintain that branch of C3, L2 and RL as looking slightly inductive here. But it does mean that we get a substantial fraction of the current of L2 being conducted by C3 and therefore not having to go back through the rest of the circuit and be conducted through Q1. It's an efficient way of using the semiconductor. One of the issues with Class E is its tolerance to changes in reflected load. And with a wireless power system, the reflected load from secondary to primary will change, and it will change for several reasons, because either I'm changing the distance between the primary and the secondary, or I'm drawing less power into the secondary because I'm charging a battery and the battery is getting close to being fully charged. One of the issues with the Class E is you can see here that I get in the first diagram here perfect zero voltage switching at turn on and turn off when the system is configured so that the reflected load is equal to an optimal value. However, if I then change that reflected load because I perhaps change the distance between the primary and the secondary, either by increasing it or decreasing it, you can see that I start to get hard switching as the drain voltage on the device starts to fall. It no longer nicely comes to zero at the point where I then turn the device back on again. A solution to that is to use what we call a load-independent Class EF inverter. This involves adding in an extra resonant branch, C2 and L2, as you can see on this slide. And we don't have a lot of time here to go into the details. You can look at some of the references here to see more detail of how this circuit works. But the extra degree of freedom that is afforded to the designer of this circuit by the introduction of C2 and L2 ultimately means that there is a sufficiently large design space now to achieve zero voltage switching throughout the entire load envelope, even as the value of RL is changed. And you can see that on this slide here. We're maintaining zero voltage switching as the device is turned on in all cases for different values of RL. The trajectory of the drain voltage now is rather different. It has some harmonic content, and it changes depending on the value of RL, but it always gets to the switching point at the same value, i.e. 0 volt. And therefore, we can maintain high efficiency even as we change the distance between the primary and the secondary. And you can see an animation of that on this slide. This is just recorded off the oscilloscope as I have a receiver that I bring up and move away from a wireless power transfer system. And you can see the yellow there is the voltage equivalent resistor, always maintaining nice 0 volt. I also, with this circuit, can achieve constant primary side current, which is very useful because I then have a constant magnetic field generated. Just to briefly talk about rectifiers. So the receive side of the link is very important, of course. It's half of the link, and it has half of the magnetics and half of the electronics. There are options, as you've seen in the previous talk, as to whether to tune the receiver as being series tuned or parallel tuned, and there are optimal loads that can be applied in order to maximize the efficiency of the magnetic link. And you can see the formulae for those on this slide. One of the main issues, however, with the tuning here is what is the reflected impedance from the secondary circuit back to the primary circuit? And that's one of the key differentiators between tuning in parallel or series for the secondary side of the circuit. If we use series tuning, as you can see here on this diagram here with the ideal circuit representation, with coupled inductors and a series tuned secondary, and then the equivalent circuit representation with a reflected resistance back to the primary. If you work through the maths of this with series resonance, then you can tune the system so that even if RL changes, the system is purely reflecting a real impedance back to the primary. In other words, I can tune a secondary resonance system. I can change the value of load resistance to change how much power flows through the system, and changing RL does not detune the primary by reflecting more reactance. It only reflects a resistance. And for that reason, we tend to use series tuning in most of our work at high frequency. With parallel tuning, this is not the case. With parallel tuning, if you change RL, you will also then start to reflect some residual reactance back to the primary, and you will detune the primary circuit, and you will lose soft switching capability on that circuit. Of course, you don't want to just simply put a resistor there and heat up a resistor. You want to rectify the AC first and get a DC to be able to charge battery or power some electronics. Various technologies you could use: current-driven or voltage-driven topologies, and you can see here topologies that some of which will be very familiar to you, used at low frequency as well. People do tend to also look at these sorts of circuits in IPT. One of the things that makes these circuits quite tricky, as they are shown here, to operate with IPT is the reverse recovery of the diode and the parasitic capacitance of the diode. So instead, we tend to try and use solutions that wrap capacitors around the diode as part of a resonant circuit, so that we are no longer suffering from the reverse recovery loss of the diode. We try and make this a resonant process rather than a hard switched, very fast recovery process of the diode. And then we're not dependent on variations in diodes and variations of capacitor junction capacitance with voltage during the circuit operation. So we end up with these sorts of circuits here. You can see that numerous versions of these resonant topologies here end up placing capacitors in parallel with the diode, so that we swamp the non-linear capacitance of the diode by a known linear capacitor, and that helps us maintain tuning of the system over a very wide range of power throughput. I want to talk just very briefly. I'm aware that I'm approaching the end of my time slot here. Regulations I mentioned are an issue here with wireless power. ICNIRP is a body, International Commission on Non-Ionizing Radiation Protection, and it looks after human body exposure essentially and sets sensible limits for exposure of the human body to magnetic and electric fields. Just as I say, there's a dedicated talk on this later on, but ICNIRP and also the IEEE set standards of safe magnetic fields. You can see that here. This is the 2020, the recently updated set of limits of magnetic field against frequency, and you can see that we're actually at pretty low magnetic field strengths here. It's actually in the microtesla when you start to get into the low megahertz range. First rule of thumb, however, the H field limit drops as 1 over omega. The received voltage goes as m omega times primary current. And so as a first rule of thumb, the received power is independent of frequency if the system is operated to the ICNIRP limit. In other words, as long as I'm on the part of the curve of this limit diagram here, where the magnetic field is dropping off as 1 over omega, then I should be able to, at every point on that curve, by operating at that limit, even as I sweep the frequency, I should be able to get the same power throughput in a wireless power transfer system. Okay, in just the last couple of minutes, I'm just going to show you a couple of videos on applications that we have done with high frequency wireless power. And I mentioned to you that light weighting is a key capability here of these high frequency systems. And one of the things that we've done is to indefinitely fly a drone. It's tethered here with a piece of nylon, but that drone there is flying in a magnetic field created by one of our Class EF inverters, and the system is light enough weight because of the high frequency that the drone is still able to fly, as you can see, and hover quite a long way above the charging pad and move dynamically over that charging pad. We've also worked on scooter charging, and you can see here in my laboratory a ride-on electric scooter. This is actually a scooter made by a company called Govex, and you can see here that we've got a GaN-based inverter, and we're charging this scooter at about 600 watts, copper coils, and we're able to get high efficiencies over a relatively large air gap to coil diameter ratio, operating the system at 6.78 megahertz. So 700 watt system input, 600 watt system output into the bike, 85% efficiency. Useful because you don't have very much payload capability on an electric scooter. You have a lot more payload capability on a full-size car than you do on an electric scooter, and that's why these megahertz systems again can be quite useful in these types of applications. So just to summarize then, we use high frequency IPT in order to be able to get lightweight coils and achieve large air gaps and freedom of movement. And also we can maintain good efficiency over these changes in operating envelope. We typically use Class E or Class EF types of inverters. They typically outperform the Class D type solutions, and if they're designed properly, they can achieve soft switching over a very wide load envelope. Rectifier choice, of course, is important. I didn't have very much time to talk about rectifiers, other than to say we favor the use of resonant type topologies again with the rectifiers, so that the parasitic capacitances of the diodes does not detune our systems as we change our throughput level. And the applications for high frequency IPT are wide ranging, and I think they're quite exciting. Thank you very much for listening. Just thanks to a number of people in my laboratory that have contributed to this talk. And I'll leave you with some references. These are references from my lab, but they cover the main aspects in more detail of what I've talked to you about today. Thank you very much indeed.